All right. So I have my same syllabus notes as before, basically. So the last part of the class, it's very dense. We have 11 lessons here, covering a lot of material. So the last homework 5, covers lessons 33 through 43. All right. Some of these are kind of short, some of them are longer. All right. And we'll be discussing the homework on the 2 sessions as usual. And this will be due the day after the last day of class. The last day of class is Monday, December 14th. This homework will be due Tuesday, December 15th. And in the meantime, of course, we'll be grading homework 3 and 4 as well. Okay. Uh, Now, a couple of comments. First of all, remember that on my website, here. On my website, the Math 119 website, remember that I do have a formula sheet. If you, for example, I would hand these out before an exam, and I would attach these to exams in class when we're on campus. Formula sheets. The formula sheet for the final, right, has all these formulas. So if you want a single file that has these various complicated formulas and ideas, this kind of it's kind of like the thing you'll see in those kind of cardboard pullouts in books. It's kind of a handy sort of reference guide for the last part of the class. All right. Also, uh, I sent out a link regarding course evaluations. So if you could fill those out and do those by Friday, December 4th. Of course, it has no impact on your grade, but it's information on how to improve the class, perhaps. All right. So, any general questions before we begin? We have lots to talk about, and I welcome questions in chat. Again, I welcome questions in chat because I'm sure that's some not cheat chat chat. Okay. All right. And I'm sure that you'll have some questions here and there. All right. So let's begin then. We have much to do today. Let's begin. Or and by the way, we're doing lessons 35 through 38. More hypothesis testing. Okay.
Hi, everyone. So today we're going to talk about hypothesis tests for mu, our old friend, a population mean. Lesson 35. Is the population mean here or not, basically? All right. So assumptions. In this lesson, we'll perform hypothesis tests for a population mean mu under these assumptions. Well, assume that the population standard deviation is unknown, because we're going to get straight to the point. We're going to start with T-tests. Get straight to the point, the more practical case. We're going to assume that the central limit theorem applies, which means that we're assuming one of two things. Either the Big Daddy distribution is about normal, or the sample size is big enough so that we eventually get normality in the distribution of sample means. Okay. Now, if sigma had been presumed known, then we would have used a z-test statistic. And it would have looked like this. Then z equals the sample mean that we get from our sample minus the mean for the x-bar distribution over the standard error. X-bar, again, the sample mean that we actually get in our sample. So this is from what we see in our sample. And then over here, well, x-bar minus mu. Now you might say, well, wait, well, we don't know what the population mean is yet. That's the whole point, isn't it? Well, yeah, but remember, we're assuming that for now that we know the value of mu under the null. We're assuming for now the null is true. So as we perform calculations, we're assuming that the null is true. And the null here will say that mu takes on a certain value. So this is the what's the reference value, basically? It's the hypothesized value for mu, the population mean, based on the null. Because we're assuming for now that the null is true. And then down here is the standard measure of spread based on the CLT, sigma over root n. Now that's if sigma were known, and that's where we would use a z distribution. But unlike with confidence intervals, where we actually mess with z for a test for a deal for mu, let's get to the point, because sigma typically is not known. Let's get straight to it. We're going to do a T-Test statistic where we presume that sigma is known. Or sorry, I'm sorry, sigma is unknown. Okay. This is a more practical procedure because typically sigma is unknown. All right, now notice, compared to the z-test statistic here, the t-test statistic looks the same, except that we're assuming that sigma is unknown. So because of that, instead of sigma, we use S, the sample standard deviation. So X bar, S, and N are all sample statistics from the sample. We get N even before we draw the sample. Okay. Where mu, of course, as usual, is obtained under the null. Remember, there are infinitely many t distributions. We use the one on n minus 1 degrees of freedom. All right. So let's do an example. Next time.
Yeah, so it's a good pause here. Any questions before I proceed? Okay, again, feel free to put questions in chat. I'll address questions in chat. Okay, any questions? Any questions? All right, let's look at an example.
Okay, so let's start with an example. Example 1, hypothesis test for a population mean, where we assume the population standard deviation is unknown. All right, a large class takes an exam. Assume that the scores are approximately normally distributed, which means what theorem applies? CLT, or the variation we need for the t distribution. We randomly sample 7 exams, and it's good to know what these pieces are. What's the 7? It's n, our sample size. The sample mean, what's the notation for sample mean, by the way? It's x bar, all right? The x bar is, x bar is 67.5 points. Put that over here. It's good to indicate these things so you don't have to keep rereading the problem over and over again. The sample standard deviation is 3.2 points. 3.2 points. That's S. If we're assuming that we don't know the population standard dev, we better at least have the sample standard dev. Test the claim that the average exam score for the class is less than 70.0 points at the 0.05 significance level. Now, before we go on, imagine this scenario. So I'm a professor of a large lecture hall class with 1,000 students. I look around, and I see that they're sweating. They're sweating, they're nervous, they're cursing under their breaths, right? And I turn to my TA, Igor. Igor is my longtime TA. And I tell Igor, you know what, Igor? I don't know if these people are going to pass this exam. I'm not going to curve the grades. It's out of 100 points. I don't know if these people are going to pass the exam. So I tell Igor, I'd like for you to grade some exams. After the exams are turned in tonight, for an hour tonight, I'd like you to grade 7 of these exams randomly, random sample of 7 exams. Do a statistical analysis on that sample, and tell me tell me what to do about my claim that the average exam for the class is less than 70 points, because I don't think these people are going to pass. I'm claiming to you, Igor, that these people overall are not passing the exam. I think that mu, I think the average exam score is less than 70 points. That's what I claim to you, Igor. Test that claim based on your sample tonight. So Igor, at the end of the exam, Igor grabs the, well, he says, yes, master, to me. And he says, he takes the stack of exams, all right, throws them up in the air, and randomly grabs 7 of them as I hide under my desk. Probably better to use a random number generator. He grades the 7 exams, does some basic data entry on Excel, and finds that the sample mean for the 7 tests is 67.5 points, and the sample standard dev is 3.2 points. We saw how to do that in the first part of the course. All right. Oh, and the 0.05 significance level, remember? Fishy, alpha. Okay. Rounding instructions vary, but here we're going to round off to 5 sig figs or sig digs, except we're going to round off the T-Test statistic to 3 decimal places. If you round off to 5 sig figs, you should be good in our class. Okay, so we're going to need these hints about the t-distribution on 6 degrees of freedom. Remember, if the sample size is 7, then the number of degrees of freedom we're going to need will be 6. And I'm not going to trick you on this. I'm not going to say, oh, I tricked you. I gave you the wrong number of degrees of freedom here, so no credit. No, I'm not going to pull a stunt like that on you. This will be correct. All right. Now, this picture also hints at something here, but I'll get to that later. Solution. So let mu be the population mean exam score for the class. It's good to officially state that somehow, or perhaps you could label that over here. Average exam score for the class. That's mu. Good to indicate what mu is. We should write it out. Okay, the methods of this lesson apply because, well, we're doing a test for mu. We're assuming sigma, the population standard dev, is unknown. So it's going to be a t-test, not a z-test. And we're also going to assume that and because we're assuming that the exam scores are about normally distributed, then the CLT applies. So we can use the procedures of this lesson. Remember, here we assumed the normal distribution overall for the class, the 1,000 students. Okay. Now, bear in mind, I'm not going to trick you here, but be aware of these things, right? And it's going to be a t-test, not a z-test. Here is the setup for this. It's going to be a left tail test, and we'll see why. Now, take a look at the claim. The average exam score for the class, mu, is less than 70 points. Is less than 70 points. So the claim corresponds to this over here. Now, this says that mu is less than 70 points, which is our reference point, 70 points. Now, since this does not include the case of equality, the claim here turns out to be the alternative. Which means, in this test for mu, here's a mu number line, which means that the alternative here favors lesser values for mu, smaller values for mu. So if the population mean really is 60 points or 50 points, we're in here. Remember, and so it's a left tail test. Remember, the type of test, in the sense of it being a two-tailed test, a left-tailed test, or a right-tailed test, that depends where the alternative is pointing. Here, the alternative points towards lesser values of mu. So kind of corresponding to a left tail. By the way, hint, hint, the picture here hints that. And again, I'm not going to try to trick you on the picture, right? Now, I might have a multi-part problem where I have various pictures, but I'm not going to try to intentionally trick you here. Take a look. I'm giving you a left tail probability. Hint, hint. That's okay. That's a hint. All right. Now, the null hypothesis would technically say, that mu is greater than or equal to 70 points, all right, the reference point. But again, remember that it is conventional for us to replace this symbol with is equal to. You're welcome. In part because we're going to base calculations on the notion that the null is true. In this case, the mean mu is exactly 70.0 points, although this does in fact wrap in other cases. This is the boundary case for this here. And we're going to assume for now, as we perform our calculations, that mu is 70 points. Again, it's like assuming a coin is fair, right? When we were testing for P. It's like assuming a coin is fair. Under the assumption of a fair coin, we're able to work out probabilities and do all sorts of calculations. Here, if we assume that mu is 70 points, then we know the distribution for X bar. Assuming that we trust our value for S. Assuming that S does a good job of estimating sigma. The sample standard dev does a good job of estimating the population mean.
A standard deviation.
Fishy. Alpha, the significance level, is 0.05. So it's not as lenient as a 1% judge. It's more lenient than a 10% judge, all right? In terms of rejecting the null, remember, here's alpha. We reject the null if the p-value is less than alpha. Right. So the lower alpha is, the harder it is to reject the null. And we give David more of a pass. Here, kind of in the middle, standard. We now identify the sample statistics. Okay, the sample size, which should have been really predetermined. The sample size n equals 7 exams. I told Igor, I want you to grade 7 exams tonight. And then early in the morning the next day, I'll look at your results. We want to use the t distribution on, well, if n is 7, n minus 1 is 6. We want to use the t distribution on 6 degrees of freedom. As we just identified, it was helpful that we labeled these. So when Igor grades the 7 exams and goes into Excel, Igor finds that the sample mean X bar is 67.5 points. The sample standard dev S is 3.2 points. Again, it helps to do some labeling along the way so that you don't have to completely reread the problem. Personally, I always hated doing that on standardized tests. It's good to indicate things, kind of indicate the notations, right? Makes it easier. I mean, these word problems, they can be easy to parse. I mean, it's not like an SAT word problem. You can actually break this down into very digestible pieces. Do it. Okay, so sample mean X bar is 67.5 points. Sample standard dev is 3.2 points. And we really need this because, again, we're not assuming that we know sigma, the population standard dev. We need at least the sample standard dev, S. And we're going to use a T-Test statistic right here. We now compute the T-Test statistic. That formula I showed you, right? Based on the central limit theorem and the fact that we're using S to approximate sigma. Remember, the fact that we're using S to approximate sigma, that's why we're using a T, not a Z. All right, here's the formula. The sample mean, X bar, the sample mean that Igor actually got from the 7 tests, his Excel worksheet, 67.5 points. Minus, now remember, we're plugging in the value for mu under the what? Under the null. Okay, under the null. The null says mu equals 70 points. So this is under the null. this here, the 67.5, that's based on our sample. From sample. It's a sample mean from our sample. Sample mean minus the hypothesized value for the mean under the null, all over S, the sample standard deviation, 3.2, over the square root of n to 7. On your calculator, you might want to work out the numerator and the denominator separately to avoid confusion. Otherwise, you might have to use a bunch of grouping symbols, right? Remember, if you were to put this all in on a calculator, you'd want to put this top, the numerator, in parentheses, and this bottom, the denominator, in parentheses. Again, I might suggest calculating the top and the bottom separately. And we're going to 5 sig figs. My recommendation here, right? Round out to 5 sig figs or sig digs. In the middle, round out the T-Test statistic to 3 decimal places. Okay, so over here, when you do this, it turns out you'll get negative 2.067 as your test statistic for T. So this is, okay, the T-Test statistic that tells us about our sample and how it relates to the null. If the null is true, how unusual is our sample results? If the mean for the class for all 1,000 students when Igor is done with the grading for the entire class, right? If the population mean does in fact turn out to be 70 points, okay? How unusual would this test statistic have been? Oh, now many of you might go, oh gosh, I think it's going to be so easy for me to fumble on my calculator. I understand. But remember, hints can help. Hints can help. I'm not trying to be hard on you folks. Hints can help.
I'm not coughing on purpose. By the way, coughing on purpose.
Hints can help. But you do have to show work, okay? I mean, don't just use the hints. I don't want you to just use the hints. You have to show me the work. You must show me this. You must show me this. On homework or any exams, you must show this. Bear in mind, you don't have to write this out if you write this out. I would recommend writing both. And write all this. I do recommend you write all of this. All right. Now, okay, so this T-Test statistic, again, is a measure of how unusual, right? It will help us measure. Well, it's a metric. It will help tell us how unusual our sample results are. Okay. Assuming that the mean is in fact, the population mean is in fact 70 points. A p-value would help. We now find the corresponding p-value. A probability will attach to the sample. This p-value will tell us what's the probability of getting at least as unusual a sample. I'll write this out, then I'll type it out. It's been a while. P-value. What is the probability that, I'm going to need a smaller font. What is the probability that we get sample results at least as unusual as what we got, namely that X bar, the sample mean, was 67.5 points. That was that number up here, remember? Okay. What is the probability that we get sample results at least as unusual as what we got if the null were true? Assuming that the population mean is 70 points. So if the population mean were in fact 70 points, what's the probability that we get something as unusual at 67.5 points is a sample mean for a sample of 7 tests. All right. And the idea is that if this p-value is really low, if it's kind of like if the null is saying the coin is fair, we flip the coin 100 times, and we get 10 heads on 100 flips. 10 heads on 100 flips. What's the probability of getting something at least as unusual as that if the coin were in fact fair? Well, if you're getting 10 heads in 100 flips, you're going to have a very low p-value, right? It's very unlikely you're going to get something as extreme, something at least as extreme as 10 heads, whether it's one-tailed or two-tailed for that matter, if the null were in fact true, okay? Likewise, if the mu were in fact 70 points, right? Well, what's the probability of getting something at least as extreme as this kind of a t-test value if the null were in fact true? This is what we're getting from our sample, okay? And what's the deal? Either our sample is really unusual or the mean was false. And so since we're taking a random sample, right, we're assuming that we're taking a simple random sample, there's no reason for any inherent bias. So if we have to choose between, if we have to choose between the sample was really, really, really unusual just by pure chance. Oh, we just happened to get 10 heads on 100 flips from a fair coin. It was a fair coin, but we just got really, really, really unlucky with the heads. If there's a choice between that, right? Null is true, but we just got really, in a way, unlucky, maybe. Or are we going to determine that the null was messed up to begin with? The null was basically wrong. So again, if we flip a fair coin, okay, if we were to assume that the coin were fair, right, and we got 10 heads and 100 flips, so what are we inclined to think? Are we going to be inclined to think, wow, it's just a heavy tail day. It's just one of those days where it's a whole lot of tails. But I really think it's a fair coin. Are you going to think that? Or are you going to think, there's something up with this coin. It's a biased coin. Well, we're probably going to think it's a biased coin, okay? So likewise over here, okay, if this is too ridiculous, then we're going to say, there's no reason to think it's a biased sample. You know what? We're going to dump this null. Anyway, we now find the corresponding p-value. It's a left-tailed test, so we need a left-tailed p-value. All right, use the hints. Our test T was negative 2.067. It turns out that the left tail probability for this left tail test was 0.0421. I'm not going to be mean and give you the right tail just to be mean, although I may have a multi-part problem with multiple hints. But the p-value, the left tail p-value is 0.0421, about 4%. All right, 0.0421. Let's compare that to alpha, our significance level. This is the p-value. Is the p-value low or not low? Is it less than alpha or greater than alpha? That's about 4%. This is 5%. It's a bit close, but the p-value is less than alpha. In that sense, the p-value is low. The p-value is low. Remember the rhyme. If the p-value is low, the null must go away. What do we do with the null? What's our decision? We reject the null. That's our decision. The decision desk on election night. Null loses. We reject the null. Finally, we write our conclusion relative to the claim. All right. We reject the null. Is that a strong result or a weak result? It's a strong result. It's a strong result. So there is sufficient evidence, not insufficient evidence. There is sufficient evidence of what? Well, what was the claim? The claim, remember, was the alternative, that the mean was less than 70 points. I looked around, I saw the sweating, cursing students, and I said, these people aren't passing. These people aren't passing for the most part. Maybe Igor's brother's passing because Igor's a TA. No. All right. The alternative is the claim. So it's like the research hypothesis. Hey, I'm a professor. I do research, right? I don't, but all right. The alternative is the claim. Can we prove the research hypothesis? We're weighing evidence for the claim. We're weighing evidence for the claim that the average, see the claim's right here, that the average exam for the class, mu, is less than 70 points. So conclusion, the final conclusion, what we tell, well, I do know statistics, but Igor still wants to give me the layperson's final conclusion. We should write complete sentences at the end. This is, especially nowadays, in these days of Common Core. Final conclusion, there is sufficient evidence for or in support of the claim that, what was the claim? You might even want, if you're rushing on an exam, you might even want to star the claim. Let's put this in red. The claim is that the average exam score for the class is less than 70 points. That's all the claims star. There is sufficient evidence for or in support of the claim that star, the average exam score for the class is less than 70 points. So remember the overall context. And we are done. Yeah, okay. Remember the overall context. I'm the professor. I am the professor. I look around, I see my students sweating and cursing on the exam, all right? I turn to Igor, my TA, I say, Igor, I don't think these people are passing for the most part, and I'm not going to curve the scores or grades. I think the average exam score, the population mean for the class, will be less than 70 points. I claim that mu is less than 70 points. So again, Igor takes his random sample, grades the exams, does the Excel thing, finds the sample statistics. We knew n was 7. Let's say I tell Igor, randomly grade 7 exams tonight. I tell you the sample size, randomly grade 7 exams tonight. Igor says, yes, master, I will do that, because Igor does everything I tell him to. Yeah, he's going to wash my car this weekend, if I needed a car, really. I mean, all right. Okay. And okay, so I see the sweating students. Igor gets these sample statistics. Okay, we run the hypothesis test. So even though I think that the students didn't pass, for the purpose of calculation, we're going to assume that mu was exactly 70 points. This is for the sake of argument, okay? So it's like a fair coin. If the mean were in fact 70 points, okay, that's like the borderline case, right? The population mean could have been 71, 72, 73, but we're going to take the borderline case, 70 points, okay, as our hypothesized assumed value. So under that assumed reference value from mu, 70 points, how unusual is this sample? How unusual is this sample, given that we got these sample statistics under n equals 7, given that we got these sample statistics, how unusual was our sample? Well, let's say that the population mean were in fact 70 points or higher. Let's just say in fact, overall, on average, the pass is passing. Basically, we want to ask, so the fact that Igor's sample, the 7 tests that Igor randomly selected, okay, well, what's the deal? Again, how unusual would that sample be? Given that the sample mean were 67.5 points, the sample mean is a bit on the low side, right? If the population mean were in fact 70 points, then this would be a bit on the low side. So we want to know, well, if we're still assuming the 70 point, that the mean, the population mean, mu, is 70 points, well, how unusual would this have been, right? Could this be chalked up to sampling error? Basically, if we're assuming the null is true and we see something like this, we're asking, well, can we chalk it up to sampling error? I shouldn't have done that. Is the discrepancy from 70 points, the difference from 70 points, can we chalk that up to simple sampling error? Or no, the sample is just too messed up, too unusual. Reject the null. Reject the 70 points. Okay. See, the sample mean was 7.5 points. It's a bit low, right? How unusual would the sample be? The T-Test Statistic is negative 2.067. That may not mean much to you. Okay, so let's find the p-value. It's a left-tail test. The probability of getting, if the mean were in fact 70 points, and if, see, the thing is, if Igor had gotten a sample mean of 70 points, the T-Test Statistic would have been 0, all right? But yeah, the sample mean that Igor got, 67.5 points, was a little low, was a bit low, okay, and the T-Test Statistic is negative. The probability of getting something that's as low as this or lower than that just by chance, like with the coin, if you assume a fair coin and you flip the coin 100 times, okay, if it were a fair coin, how unusual would it be to get 10 heads or lower? Likewise here, if the true mean were in fact 70 points, okay, how unusual would it be that just run a random sample, we get a sample of 7 tests with a t-score of this or lower? It's about 4%. Is that low? Yes, it's lower than alpha. It's too low. It's just too low. So we reject the null. So it's like getting 10 heads. This really is like the situation where it's like 10 heads. The left tail probability is just too low, all right? Which means that if we have to choose between, oh, well, the mean was in fact 70 points. We just got, this sample just got really unlucky. Or, it's too unusual. The null was wrong. The coin was not fair. We're going to go with the null was wrong. The coin was not fair. The mean was not 70 points. There is sufficient evidence for my claim that the average exam score for the class was less than 70 points. So when I told Igor, I don't think this class is passing. All right, I think they're failed the exam, basically. Well, based on this hypothesis test, because of Igor's sample and this test, we now have, even that night after Igor grades the 7 exams, he doesn't have to grade all 1,000. Then we have a census. That night when Igor grades the 7 exams, all right, and then I wake up at noon, all right, and I ask Igor, what's the deal, right? Igor says, Master, there was sufficient evidence for your claim because you're so awesome. There is sufficient evidence for your claim. You were right last night. You were right that that class is not going to pass. And then when Igor grades the 1,000 exams, it's likely that will be the case. When the 1,000 exams are entered, their scores, Igor finds the true population mean. It's highly likely that the mean's gonna be less than 70 points. All right. Next time, we've been doing the p-value method. We're going to look next time at the traditional or classical method for hypothesis testing.
So that was a really long video, one of the longest that we've had, but I was really pushing a key example. So if you got that example, you really have the key flavor for what's going on here. Any questions? Any questions? It's a video you might want to review. You might want to, fast forward, skip some parts, but you may want to pinpoint some key ideas there and review that. So remember this video, right? It's it's that long second video for lesson 35, okay? With some key ideas. Any questions? Any questions? That was the p-value approach, which is considered to be the more modern approach. The next lesson will deal with the traditional or classical approach, which old school books focused on. All right, and which I can still examine you on the homework. So do know the p-value method and the traditional or classical method. There's also a confidence interval method. All right, again, questions in chat. Let's proceed.
Hi, everyone. So far, we've been using the p-value method for hypothesis testing. And we've also looked at the confidence interval method for hypothesis testing. Now, this is often taught first in stats books, especially the older ones, but we're going to save the oldest method for last, lesson 36, the traditional or classical method for hypothesis testing. And actually, we're going to need this in the next lesson when we do two-tailed tests that involve the chi-square distribution, which were not symmetric. Okay. how can we use critical values? Remember those things from confidence intervals to do hypothesis tests? Okay, in the olden days, before computers were in common use, and well before iPhones or cell phones or anything like that, before computers were in common use, people like me had to use statistical tables and the traditional or classical method of hypothesis testing. Well, you could use the p-value method, or well, I mean, basically, you need a statistical table for any of these methods, right? I mean, whether it's the traditional or classical method, or the p-value method, or the confidence interval method, you need some sort of statistical table. All right. So we're going to use, yeah, as I said, we'll use the method for some hypothesis tests, particularly two-tailed tests in lesson 37, where we lose symmetry for chi-square, when we analyze sigma and sigma squared. All right. We're going to go back to the magician's coin, because it kind of makes sense for us to use our very familiar examples in order to describe this new method. Really, it's the oldest method. All right. As in lesson 33, example 1, we want to test the claim that a magician's coin is fair at the 0.05 significance level. Okay, maybe start this. Now we could let P be the probability that the coin comes up heads. Here's a setup. A magician's coin is fair. That means P equals 1/2 or 0.5. That's the claim. This is the case of equality. Of course, it's the null. The alternative is then two-tailed, favors both lower values and greater values for P. Two-tailed test. Alpha is 0.05. We now gather sample data. The coin is flipped 100 times, and it comes up heads 51 times out of 100. And we've done this before, right? And just think about it. Folks, think about it. David says his coin is fair. The magician's coin is fair. You flip the coin yourself, you get heads 51 times out of 100. Do you think you're going to call David a liar? Well, think about it, right? Okay, the sample proportion, P hat. So what is our best guess for what P is based on the sample? X over N, 51 over 100, 0.5100. Verify that the normal approximations apply, NP and NQ. If P is a half, Q is a half, they're both at least 5. As before in lesson 33. And in fact, you might remember this result. If you work out the Z-test statistic, right? It's a test for P, a probability. The Z-test statistic is 0.20. 51 heads out of 100, we get a Z-test statistic, a Z-score of 0.20, which is very close to 0, okay? If we had gotten exactly 50 heads out of 100 flips, then we would have gotten Z equals 0. Well, 51 heads is very close. This Z-score is very close to 0. So basically, we know right now very little evidence against the null. Very little evidence. We're probably not going to call David a liar. And before we used the p-value method, where we found the probabilities in relevant tails. In this case, well, it's a two-tailed test. So yeah, it's a two-tailed test. So we'll do this whole jazz. Positive 0.2, negative 0.2. It was a huge, huge p-value. Huge. No way we're going to reject the null. No way it's less than alpha. Now, instead of the p-value method, we will use the traditional or classical method to make a decision about the null. And on an exam, I would tell you which method to use. Both methods, in fact, I may have you use multiple methods. Maybe the confidence interval method. And both methods will yield the same decisions and conclusions. And the same for confidence intervals. Remember that confidence intervals can be applied for two-tailed tests, at least the way we've been doing it. Now, again, this is a two-tailed test because remember the alternative favored both the left and right tails. It's a two-tailed test, so we need two critical values. You know, let's show the picture right now. Well, I'll pull this up. This is a two-tailed test, so we need two critical values. Here's the general picture over here. Here's the picture that's relevant in this case. Alpha is 0.05 in our example here. All right, so this is a two-tailed test, so we need two critical values. Okay, in general, it's z sub alpha over 2 and the opposite. Okay, in this case here, here's a key hint, okay? In this case here, in our hint, we're gonna see that if alpha is 0.05, right? That's broken up into halves symmetrically, 2.5% in the left tail, 2.5% in the right tail. We get 1.96 and negative 1.96. See, before, we grabbed the z-score and we ran with it, and we found probabilities based on z-scores, or their opposites, right? But now, we're doing it more like confidence intervals. Remember, we used critical values when we were developing confidence intervals, all right? So these should look familiar. 1.96 and negative 1.96, these trap 95% or 0.95 in the middle for Z distribution. As I said, folks, 1.96, you might be thinking about this a lot. All right. These are the CVs that helped us with a 1 minus alpha confidence interval before. So we've seen critical values before, right? In this case, 1.96 and negative 1.96. What's new is the notion of a critical region, all right? So in this case, the z-scores, the z-values that are more extreme than these critical values in a tail sense, right? So the right tail over here, the left tail over here, they make up the critical region. So the critical region shrink this again, all right? Critical region. So the critical region the critical region would correspond to both this left tail over here and this right tail over here. Actually, I should lower these a bit. The critical region is technically a set of z-scores. They're not probabilities. Okay, so I should do it like that, where I'm pointing to these z-scores. I'm pointing to these, I'll put the mustache here. Moved over. Here, okay. So remember, the critical region, this is a set of, in this case, z-scores. Later on, they can be t or chi-square. Here, a set of z-scores. All right, the z-scores that are less than negative 1.96, the z-scores that are greater than 1.96. Again, on the examples I give you, you're not going to get exactly the critical value. That's no fair. The probability of that happening is 0 anyway. Okay, so the z-values, the z-values that are more extreme than the critical values make up the critical region. They correspond to the left and right tails of the z number line, and these are the shaded regions. They correspond to the shaded regions, or more precisely, the pieces of the z number line that correspond to the shaded regions. These are the z-values that would be too unusual under the null for the null to survive. Think of the critical region as the danger zone or acid bath where the null dies. So remember that for the critical region, what's the deal? The null dies here. We reject the null. So these cutesy ideas I'm giving you involve when the null is rejected. If the p-value is low, the null must go away. We reject the null. Here, if the z-score based on our sample falls in the critical region, this danger zone, this acid bath, right? A danger zone or an acid bath. The critical region, I call it a CR, right? Okay, it's like a danger zone or acid bath regarding the null. It's where the null tends to die. All right, the null dies there. If your sample z-score, if the test statistic falls in the critical region, in general, if a test statistic based on a sample, if the value falls in the critical region, then we reject the null. The null dies. Okay, that means the sample is too unusual for the null to hold up. It's like seeing 99 heads in 100 flips, and the null said, "Oh, the coin's fair." Yeah. That null goes in the acid bath. Okay. I just told you this decision rule, right? And by the way, this is the professional term, decision rule. The decision rule for a hypothesis test using the traditional or classical method. If the value of the test statistic, right now it's z-scores, if the value of the test statistic lies in the critical region, the danger zone or acid bath, then reject the null. If not, then don't. All right. So what's the deal with z equals 0.2? Well, right off the bat, I mean, you know that this z-score is very close to 0, okay? So for any reasonable value for alpha, then I don't think we're going to reject the null. But let's see it play out. Okay, so we basically know what's going to happen, but let's see this thing play out. It's like watching a predictable film. Okay, it's like watching an M. Night Shyamalan film, and you know the twist. We're going to reject the null. That's the twist. We're going to reject the... Wait, I'm sorry, no. We're not going to reject the null in this case. We're not going to reject the null. We kind of know. All right. Okay, test statistic is z equals 0.2. Remember, the critical region, the CR, I'll put that in red. Okay, so the critical region corresponds to this piece of the number line over here, the Z number line, and also this piece over here. The critical region is in two pieces. Values for Z less than this critical value, values for Z greater than this critical value. Now, and bear in mind that we were able to do this even before we got our sample. I mean, we could have determined all this even before our sample. We know it's a two-tail test. We're going to use Z. Alpha is 0.05. But now, after we get our sample, we can now find the relevant test statistic, the relevant Z-score is 0.20. Where's that? It's almost smack dab in the middle. It is safely in the safe zone. I'll put that in blue. This is the safe zone for the null. Oh yeah, this is very cushy. I mean, the null is being put on a nice comfy bed, being fed grapes and wine. Oh, the null's fine there. Come on, the null's saying the coin is fair. Okay, so let's say the coin, the head on the coin is thinking, oh gosh, am I fair? Am I fair? I hope I'm fair. All right, I flip the coin, 51 heads out of 100. That coin, that head can rest assured, yeah, I'm okay. The null is going to be safe. We're not going to reject the null. Nowhere near the danger zone or acid bath. We do not reject the null. That's a weak result. So I guess I should write this formally, right? The test statistic, which in this case was a z-score, is not in the critical region, which means the null is safe, not innocent, but the null is safe. Don't reject the null. Okay, we do not reject the null. We do not reject the null. Is that strong or weak? That's weak. There is insufficient evidence to say something. Now, the claim was that the coin is fair. The claim was the null, right? The magician's coin is fair. The claim was the null. So we put the null on trial, okay? And we're weighing evidence against that null claim. Because the null is a claim, we weigh evidence against that null claim. Putting the pieces together, there is insufficient evidence against the claim that the magician's coin is fair. And again, you think about it. David comes, sees you and says, this is my coin. I claim it's a fair coin. You flip the coin 100 times, comes up heads 51 times in the 100 flips. There's insufficient evidence against David's coin being fair, okay? So if you're wondering, do I have sufficient evidence to call David a liar? No, I have insufficient evidence to call David a liar. 51 heads out of 100, that's very much in the safe zone. The coin may very well be fair. Next up, we're going to apply these ideas to lesson 37 when we do tests for sigma and sigma squared, population standard deviation and variance. Next time.
So questions, because when we do 37, The overall steps and ideas are very similar. It's mostly different notations. The formulas look different, but the ideas are going to be very similar. Any questions? Because you might be thinking, oh my gosh, so many lessons, so many things. Actually, it's the same rhythm. Once you get the rhythm, you're okay. So once you get the rhythm, actually, this last part could be fairly easy if you get the rhythm, if and when you get the rhythm. All right. Any questions? Any questions? Because we're leaving means, we're going to go to spread, standard deviation variance. All right.
Hi, everyone. So we are going to do now lesson 37, hypothesis tests for sigma or sigma squared. You remember them? Population standard deviation or variance. Are they here? Oops. Are they here or somewhere else? Okay. The reference value is here, right? The null. Okay. Assumptions. Now remember that these tests are not as robust as before, right? We really are assuming normality. We have to assume normality, basically. It's not quite the CLT stuff we did before, even with large sample sizes. Now, we're going to deal now with a chi-square test statistic. And remember, that's why, because this distribution, or these distributions, lacked what property? These distributions are not what? They're not symmetric, or they're asymmetric. Okay, in part that's because sigma and sigma squared are never negative. Chi-square values are never negative. That's kind of helpful. They're called chi-square values because they're never negative, right? Squares of real values are never negative. Okay, and also, because we lack symmetry, it means that the p-value method is awkward if you have a two-tailed test. All right, anyway, the chi-square test statistic for tests for sigma or sigma squared, the underlying theory is basically the same for these two guys. All right, so chi-squared equals, it turns out to be the quantity n-1, which is, by the way, the number of degrees of freedom. That's not quite a coincidence, right? Times s squared over sigma squared, where sigma is, of course, obtained under the null. It's the reference value. The hypothesized value for sigma squared, or the variance, under the null. The null could refer to either the population standard deviation or the population variance. If the null refers to the population standard deviation specifically, you would square that reference value. Again, we use the chi-square distribution on n-1 degrees of freedom. Notice it's been n-1 so far for both chi-squared and t. Okay. Example. And this sounds like a comedy, especially from the 80s. A women's college goes co-ed. So it's a college that has had a long history of admitting women. It's been only women, but after some point, it admits men as well. Now, because of the long history of the college and the students have all been women, we assume that women's heights there have a standard deviation of 2.5 inches. And that's known, all right? That's the known population standard deviation for women's heights. Okay, now the men, they're kind of new. So we don't have the health statistics on the men that we do for the women, all right? I know that we're kind of assuming that the situation hasn't changed over time, but let's ignore that. Let's say that we know the deal with the women, all right? We know the population parameters for the women, like the population standard deviation. But the men are new, and we're not as sure health-wise what's going on with them. Okay, health or medically wise. Okay, so assume that the men's heights are approximately normally distributed. So we'll at least make that assumption. And remember, we needed that assumption in order to even apply the methods of this lesson. And not to say that it's totally okay for you to assume something just so that you have the right to use a certain procedure. But let's assume that genuinely, yeah, men's heights are about normally distributed. We randomly sample 20 men. And let's assume that we have a lot of men who have been at the college recently. Because remember, if little n is too close to big N, then some of these formulas have to be adjusted. Okay, the sample standard deviation for the men is 3.4 inches. So that's our value for S. Now, this is sigma for the women, right? I guess you could look at it that way. You could think of this as sigma for the women. Right, and that's known, but we don't know yet sigma for the men, right? That's what we're testing for. Okay, so we round the sample, 20 men, and by the way, 20 is going to be the value of n, the sample size. Okay, and here finally the sample standard deviation. Sample standard deviation is going to be 3.4 inches. A variance, by the way, would be measured in square inches, although that might be a meaningless unit in the context of things. So that's one reason why we might prefer standard deviation in general, because it has quote unquote normal units. It is true we might deal with variances sometimes, but one drawback to variances is that the units are often meaningless. Okay, test the claim that men's heights and women's heights at the college have different standard deviations at the 0.05 significance level. So I don't know, perhaps there might be dorms, maybe the dorms are still separated between men's dorms and women's dorms. Maybe they're doing like measuring heights of doorways or something like that and wondering what the variance, what the spreads might be, right? Anyway, okay, as far as rounding, oh, by the way, the 0.05 is then alpha. I use red here. 0.05 is our alpha, which was standard. Rounding instructions vary, but here, let's round off to 5 sig figs or significant digits, except round off the chi-square test statistic to 3 decimal places. On an exam, I would tell people how to round. I mean, I don't want you to leave this class thinking, oh, it's all rounding. That's kind of boring. All right, anyway. So use the traditional or classical method of hypothesis testing. So I will tell you what method to use, right? I might ask you to use 2 or 3 methods, right? Traditional, p-value, confidence interval. Use the traditional or classical method of hypothesis testing. And as I mentioned earlier, because we lose symmetry in the chi-square distributions, then we tend not to use the p-value method for two-tailed tests. So I would never give you a two-tailed test in this situation where I tell you to use the p-value if we're dealing with a chi-square distribution. Then we really want to use a traditional method, or maybe the confidence interval method. And here's some hints. Bear in mind, the sample size was 20, right? And it's 20, so we're going to use the chi-square distribution on 19 degrees of freedom. I wouldn't trick you there. Chi-square distribution on 19 degrees of freedom. Here's the density curve. Remember, it's asymmetric. It is not symmetric. The possible values do not go to the left of 0. Here's the density curve. It turns out these will be the critical values. These will be the critical values that trap 95% in the middle for a chi-square distribution on 19 degrees of freedom. So I think we're going to see these things later on. Okay, let sigma be the population standard deviation for men's heights at the college. Now remember, I told you that in the long and storied history of this women's college, we're assuming that the population standard deviation for women was known to be 2.5 inches. We're assuming that that's known. The men, we're not so sure about. Okay, but we're going to let sigma, which is really unknown here. If you wish, you might even want to call this sigma sub men, if you wish. Let sigma or sigma sub men be the population standard deviation for men's heights at the college. Granted, this might be kind of awkward to put into formulas. Okay, the methods of this lesson apply because remember, we assumed that the men had about a normal distribution. Or at least you accept that, right? Maybe you assume that and say in your paper, let's assume a normal distribution, roughly. Or not too roughly, but close enough. Here is the setup. All right, let's talk about this. Test the claim that women's heights and men's heights, test the claim that men's heights and women's heights at the college have different standard deviations. Now, there's another way of framing this. Okay, now this is the claim. I'll circle this. Running out of colors. What, turquoise? All right. Not orange. Okay, just to claim that men's heights and women's heights at the college have different standard deviations. I'll star it. So that on a final exam, if the student's really running out of time and doesn't have the time to write this out, I might tell the student, you know what, do this. Circle it, star, put star, do a copy paste idea. If you're rushing, right, there's like 10 seconds left in the test. Anyway, now there's a way of reframing this, right? So how can we think about this in terms of sigma, or maybe sigma sub men, right? Sigma is sigma sub men. Sigma sub men is what we're calling sigma, okay? Now, the claim here is that men's heights and women's heights have different standard deviations. So the claim here is that sigma is not sigma women, which was 2.5 inches. Sometimes in a problem like this is a red herring. You don't use this number in the problem, but it might be just a point for comparison. But here, yeah, actually, we do use the 2.5 here. All right. And that's the claim. Sigma is not 2.5 inches. Is this going to be the null or the alternative hypothesis? This does not include the case of equality. In fact, it's the only case that's excluded. Yeah, this got to be the alternative. That's the claim. And it's a claim based on the wording, right? Claim based on the wording. The claim is that sigma is not 2.5 inches. The null is that sigma equals 2.5 inches. And that is absolutely the case. There's no this stunt or that stunt. There's none of that. The null says, absolutely, sigma equals 2.5 inches. It doesn't represent anything else. Sigma equals 2.5 inches. So what kind of test is this? We look at the alternative. Number line for sigma. I mean, it stops at 0, but okay. Which tails will the alternative favor? The alternative likes both the right tail over here and the left tail over here. Bear in mind, the left tail stops at 0, fine. But it's a two-tail test because both higher and lower values for sigma favor the alternative. The null is stuck with sigma being 2.5 inches. The null covers very little territory. However, the question is, can we reject the null? That's the thing. Even though the null covers only this sliver here, technically, still the question is, do we reject the null or not? Okay, we now identify the sample statistics. And we talked about these before, right? I mentioned that up here. And it's good to label these things so you don't have to keep rereading the problem. Okay, the sample size, n equals 20. There are 20 men, and we measure their heights. We want and we need to use the chi-square distribution on 19 degrees of freedom, which means that my hint was helpful. The sample standard deviation for the men, right? I mean, the women, I don't want to say we don't care about women, but we're assuming that we already knew the deal with the women, right? That the sigma historically has been 2.5 inches, and we're assuming that's still good. It's like the ice cream problem, right? Okay, the sample standard deviation for the men that we've measured for their heights, S equals 3.4 inches. So let's compute the chi-square test statistic. Here's the formula I gave you, I showed you, all right? N minus 1, the number of degrees of freedom. 20 minus 1 is 19. S is the 3.4 here, all right? And that's squared, right? S is 3.4, that's squared. Remember that if I were to give you the sample variance, you just stick it in without squaring. So remember we have S squared here, okay? If I give you the sample variance, plug it in for here, right? That is the sample variance. But I'm giving you S, right? basically. You recognize this as S. So the 3.4, that is squared in the formula. Over, okay, sigma squared. Well, again, it's that same idea, right? Remember, we're assuming that the null is true, right? We're doing these calculations under the null. Do some green. Do calculations under the null. We're doing calculations under the assumption the null is true. The null says sigma, the population standard deviation for the men, for all the men going to the college, is 2.5 inches. Sigma alone. So sigma is 2.5, but that's squared. Bear in mind that if the null had been framed in terms of population variance, then you would stick it in without the square. To square or not to square, depends what I'm giving you, and it depends on what you see in the formula. Work this out, and it's about 35.142 to 3 decimal places. So this is a nice single number that describes how the sample relates to the null hypothesis in the context of this overall test. Okay, 35.142. But looking at it, this may not mean much to you. This may not mean much to you. So it would be helpful to look in terms of either probabilities and p-values, or just ask yourself, so how do I classify this? I mean, is this too extreme or not? I mean, am I gonna, basically, how do I make my decision? Do I reject the null or not, right? How do I determine that? Do I reject the null or not? We're going to use the traditional or classical method to make a decision about the null. Okay, so here's the hint, right? Chi-square on 19 degrees of freedom. Alpha was 0.05, remember, and it's a two-tailed test. So this picture is totally appropriate. And of course it is. I'm not going to trick you, right? But as I said before, I might give you a multi-part problem with multiple hints. So do figure things out. All right, so what are the critical values that trap 95%, okay, which is the complement of alpha? Alpha is 0.05, right? 1 minus alpha in the middle, like for a confidence interval, okay? It's going to be the 8.907, that's the left critical value, and the 32.852, that's the right critical value. They don't go plus or minus like they did for T or Z. Okay, so I'm giving these critical values, and I'm also giving you the critical region. It's in 2 parts. So we have a piece of the critical region over here, and a piece of the critical region over here. So how do we make our decision? Well, here's the critical region. Is the test chi-square value in the critical region or not? Is it in there or not? And remember the deal. It was this here. Okay, well, and then let's, as a reminder, as a two-tailed test, we need 2 critical values. This over here is chi-squared sub L. This here is chi-squared sub R, left and right critical values. Okay, chi-squared R and chi-squared L are the critical values, right? The chi-square values that are more extreme than the CVs make up the critical region, and they correspond to the left and right tails over here. I just repeated what I just said. I mean, okay, now the question is, well, is the test chi-square in there or not? The test chi-square based on our sample was about 35.142. 35.142, look here, 34, what was that? It was 35.142, whatever. 35.142, look at this. Is 35.142 your test chi-square from your sample? Is it in the critical region or not? It is in the critical region, kind of barely, but yeah, it's over here. Okay, so the chi-square value is about 35.142. It is in the critical region. That's the danger zone, the acid bath for the null, or regarding the null. This is the danger zone or acid bath. as far as the null is concerned. What do you do with the null? We reject the null. Okay, lies in the this lies in the Kronecker region. We reject the null. Is that strong or weak? Is that a strong or weak conclusion? Reject, strong. Will we have sufficient evidence or insufficient evidence to say something? We will have sufficient evidence to say something. It will be a statistically significant result. The final conclusion, we reject the null, so that's a strong result. There is sufficient evidence to say something. Who is the claim? The claim was the, I forgot too, actually. It was the alternative. Okay, I remember. It's the alternative. Okay, so it's like the research hypothesis again. Can we prove the alternative? We're weighing evidence for or in support of the claim that, right? Star. That was the star guy. Right? Up here. Way up here. I started, right? Way up here. So if you have like 10 seconds left in the test. Teacher, you know what I mean. And seriously, I would, but okay. The alternative is the claim. Okay. So conclusion, put them together. There is sufficient evidence for or in support of the claim that men's sites and women's sites at the college have different standard deviations. So if we're a doctor and you're looking at some data, you're thinking, you know, I'm claiming that they're different, the men and the women, with their different SDs or different measures of spread. And there is, in fact, sufficient evidence that you're right. You're a smart doctor. Whether you're a man or a woman, you're a smart doctor. All right. Next up, mistakes. Think about a jury trial. In a jury trial, what do we mean by a mistake in a jury trial when it comes to the verdict? Next time.
Any questions? And let's take a moment and think about that. Okay, you can even put some things in chat. Actually, last semester, we had an interesting talk about that. So when I say that we're going to talk about mistakes in a jury trial, what are the mistakes that can be made? Think big. When does a jury make a mistake? When is there a wrong verdict? Give me a moment. Depends on what the deal is with the defendant, right? So maybe you can come up with one of these. When does a jury make a mistake? I was actually up for a jury duty a couple weeks ago. Managed to get out of it. When does a jury make a mistake? If the defendant is what and the jury says what? When does the jury make a mistake? If the defendant is what and the jury renders a verdict of what? Well, think about it. We're doing that next.
All right. When do we make errors? Because sometimes we'll make mistakes. We may not ever know. We might not ever know the value of mu or p or whatever, but sometimes we will make mistakes. So the jury trial analogy. What's the deal with type 1 and type 2 errors? All right. When do we make a mistake? When do we make a mistake? First of all, when do we not make a mistake? When do we have a correct verdict? All right. Well, we get a correct verdict if an innocent defendant is found not guilty. That's a correct verdict. Also, if a guilty defendant is found guilty, right? That's a correct verdict. So what are the errors that can happen? And maybe your politics might come in terms of which is worse. Type 1 error. That's when a defendant is innocent, but is still found guilty. Type 2 error, that's when the defendant is in fact guilty, but is let go, is found not guilty. Now, type 1 error is the one that we tend to focus on more in statistics, the idea of convicting an innocent defendant, which in real life would be very, very disturbing for us. Type 2 error would be maybe impractical in some sense, but type 1 error, the idea of convicting the innocent, although I don't know, some people are more bothered by type 2 error, right? Different judgments. But in statistics, maybe because I was trained as a statistician, convicting the innocent, that's the type of error that we tend to focus on. Right. Now, instead of a jury trial, let's think of actual statistical testing, hypothesis testing. The null as the defendant. All right. When do we make a correct decision? If the null is true and we don't reject it, that's a correct decision. Or if the null is false and we reject it, that's also a correct decision. Now, where are the errors? If the null is true, but we reject it. Type 1 error. David might say, my coin is fair. We say, no, it's not, but maybe he was telling the truth. So you hurt your friend. Then there's type 2 error. The null is false, but you fail to reject it. Okay, if the null is false, then the correct decision would be to reject the null. If you don't reject the null, that's type 2 error. So that's the case where David's lying, all right, or he doesn't know his coin. David's lying. The coin is in fact biased. The coin is in fact biased, and you don't reject the null. So maybe the coin is actually a 55% head coin, right? You flip the coin, you get 53 heads out of 100. You might not reject the null when the null should have been rejected. Still, you applied appropriate statistical practice because you took me, right? All right. We commit a type 1 error, again, when we reject the null, even though the null is true. It's like convicting the innocent. Type 1 error, convicting the innocent, null. Convicting an innocent, null. In fact, the probability that you will reject the null, given that the null is true, the probability that you reject the null, given that the null is true, is alpha. That is the significance level. Another way to look at that is the probability that we convict, given that the null is in fact innocent. Probably that we convict, given in fact that the null is innocent. Type 2 is when we do not reject the null, even though the null is false. So that's the, well, let's not go there. All right. Interpreting alpha, we just said that. So in the example of testing the claim that a magician's coin is fair at the 0.05 significance level, two-tailed test, we've done this before. Now, let's assume the null is true. Let's assume the coin is in fact fair. We could still get unusual sample results by chance to the point where we could end up rejecting the null, thus committing a type 1 error. For example, a fair coin could conceivably come up heads 100 times in 100 flips. It's very unlikely, and I'm sure we'd be rejecting the null in that case, all right? But if the coin is in fact fair, we're committing a type 1 error. We're convicting an innocent null, an innocent coin that's really fair. Now, 5%, what's to do with alpha? 5% is the chance that our test statistic will be in the critical region, okay, corresponding to the shaded region below. So alpha is 5%, corresponds to the total combined tail probability in the two pieces here, all right? And remember, we reject the null if our test Z is in here or here. So if the null is in fact true, then the probability of getting something as extreme as this, at least as extreme as these guys by chance, is 5%. That's alpha. 5% is alpha. So again, if the coin is in fact fair, okay, alpha is 5% is the probability that we reject the null even though the coin was in fact fair. Okay. All right. So that's that.
Okay, so that is that, right? Yeah, so we're at 9:35. Wow, I'm on time. That's rather unusual for me. All right, we're on time. We covered a lot though, right? We covered 35 to 38. But again, folks, if you got the rhythm of the hypothesis testing, right, it wasn't too bad. It's a matter of getting the rhythm. Okay. Again, course evaluations can be submitted by Friday. We'll finish up all this stuff on Monday, and there's no rush. I mean, if I have to go a little bit into Wednesday, that's fine. We don't have to rush these, right? In the meantime, keep up with the homework because we're going to start talking about it, especially next Wednesday. Any questions? Any questions? Whoa, okay. Right. Yes, and I agree. You might want to go back and rewatch the video, especially that 30-minute video number 2 from today, right? Day 28, video 2, that key example, right? And you can skip around in that. So for many of you, I'll see you on wow, Monday already, right? Hard to believe. Yeah, I'll see you on Monday, December 7th. Otherwise, I will stick around for questions. Okay, so for many of you, have a good weekend. All right. Remember to do the homework and the course evaluations, and I'll see you Monday. But I will stick around for questions. So please let me know if you have any questions. I'll go ahead and shrink this now. By the way, I'm starting to add this video because that helps me order the playlists. The playlists are ordered according to my last video, so I got to add this sometimes. Technicality. All right. Okay, so have a great weekend. Some of you may want to stick around. All right. Any questions? Any questions? In fact, let's do this. I'll come back at 9:40. All right. So at 9:40, I'll come back and check on you and see if you have any questions about the class in general, homework questions. I'll come back at 9:40. Otherwise, have a great night and weekend. All right. I'll pause this.